We're down to the last hour or less of the day. I'm kind of lost my place, but I'll get it as we get moving. So we're going to review quickly the laser absorption theory on our way to using laser absorption in shock tubes. That's what we're going to do. And the governing equation is Beer-Lambert law, which applies only for monochromatic light. We can write it in different forms, but usually I write it as SV mole fraction times static pressure times L. So it's SV P sub I times L. We conduct this across the shock tube, which we take to be uniform and of diameter L. We have to know the line strength. We have to know the line shape. It looks like this. Where do we get this line strength? It depends. It's a function only of temperature. So we do an experiment where we know the temperature. Therefore, we know S. Knowledge of this comes, maybe we'll scan our laser and we'll measure this and store it in a table. So we'll know this as a function of T. And we'll know the path length. We'll measure the static pressure. We'll solve for this. Most of the time, we're solving for the time evolution of the mole fraction of the absorbing species. What species have we measured? And so we started this maybe in mid-70s, maybe. And over time, we've learned how to measure a lot of species in ultraviolet, the visible, and the infrared. And each one of those wavelengths was chosen by looking at the spectrum and finding the most attractive line. So we've done the spectroscopy that we've been talking about. We look at the spectrum, figure out what wavelength we want to use. These are the wavelengths. And then we have to measure or know the cross sections or line strengths at our temperatures. So there's a lot of work that goes into this. Sometimes we'll work a year, maybe 2 years. Do I have formaldehyde here? Okay, so recently I've got a student who's working on formaldehyde, CH2O, and acetaldehyde. He's been working on it for 2 years. So 2 years to figure out what wavelength should we use, what's the absorption coefficient, if there's overlapping spectra, how do we deal with that problem. Now, probably 2.5 years, maybe 2.5 years, he's ready to use this technique. In 1982 or so, we first started to make use of tunable dye lasers. So early on, we used tunable infrared lasers like an electric discharge CO laser. We started to get into tunable dye lasers around 1980. That was how we got access to the ultraviolet. We still use one of those original lasers, spectrophysics 380. So it's a CW ring dye laser. It just means that the cavity is a ring, and the light goes around and around in that cavity, and it's monochromatic. And then it's hard to work in the UV. The lasers are harder to deal with. Infrared's pretty easy. So finally, we got a big hunk of money, and we bought a Ti-sapphire solid-state laser that gives us easier use in the UV. And that's called DeMira, Ti-sapphire. So it pulses actually at 80 megahertz, but it acts like it's CW. So we treat it like CW, but it's actually pulsed. Then starting about 5 or 6 years ago, we started to get access to a lot of these new infrared lasers, diode lasers that we've been using. Here's a couple of Nova wave lasers. They must be about 4 or 5 years old now, probably, which are tunable infrared lasers. So you might ask, well, how? So we do some work to figure out what wavelength should we use to measure NH2, 597. How sensitive are these techniques? Here's some plots showing that for fairly big molecules, here's methyl, NH2, so on, ppm. This is the detection limit, meaning signal noise ratio of 1. For 1 atmosphere, 15 centimeter diameter shock tube, 1 megahertz bandwidth, which means we record with microsecond time resolution. So what you see is that for methyl, combustion range here, we're at a few ppm. CO2 is not quite so good, maybe 100 ppm. So the sensitivity depends upon the species. These are infrared transitions. This is a UV transition. The UV transitions are stronger. This is a visible transition. So as you go to longer wavelengths, the detection limits go up, but there's usually plenty of CO2 to do this. Now, here's what you get if you go to diatomics. Same kind of system, 1 atmosphere, 15 centimeters, 1 megahertz, temperature, detection limit in ppm. So CN, this is my favorite. This has a very strong oscillator shrink. The oscillator shrink is 50 times larger than one for OH. That's the FEL. CH is in between. So at combustion temperatures in here, we're tens of parts per billion. We're still less, but this is a noise ratio of 1. So a good experiment for us, we'll design an experiment with 10 or more ppm of OH. More is okay. CO, that would be the fundamental. That's an infrared transition, so that's why it's a little higher. So anyway, we know these numbers. We can design experiments so that we'll have the right amount of reactant. And the hard part usually is there's maybe 3 species you want to measure and they don't have the same sensitivity, so sometimes that's a little tricky. Okay, I'm going to show you 3 examples, 3 types of experiments. I'm going to call this one the foundational fuel. These are elementary reactions. How do we measure an elementary rate constant? Elementary reaction rate coefficient. Those are the gold standard. You have one reaction, you measure something, you determine it forever. That's the ultimate. Very hard to find a way to do these. But I'm going to show you a couple of successful examples. So in the hydrogen oxygen, actually this is the so-called foundational chemistry. So there's a lot of interest right now in small molecules and measuring the elementary rate coefficients for those small molecules and getting them right. Untuned, just get those right and put them into a model. Starting with this one. So I'm going to give you 2 examples. This is the important one. It always shows up as perhaps the most important, but I'm going to show you a new result on this one. How do we do this? It's kind of a 2-step process. We use sensitivity analysis and some knowledge of the chemistry to design an experiment in which ideally the reaction is isolated. Means what's the temperature, pressure? The variables are temperature, pressure, mixture, and the thing we measure. And you want to pick that so that you can be sensitive to one reaction, ideally. We use the shock wave just as a heater. Here's an example. This is the one that you will have seen in Professor Pilling's lecture if you went there for this branching reaction. Now, we did this years ago using UV absorption, but I had a student who was very clever about 4 or 5 years ago, Hong, who figured out how to do this in a new way. So here's the reaction. And surprisingly, what we measured was H2O. So if you look at the 1500 degrees, 2 atmospheres, excess hydrogen. So 10 times as much, 9 times as much hydrogen as oxygen. And then you do a sensitivity analysis, and so this is the sensitivity to H2O of certain reactions. So this red line says that for H2O, the dominant reaction is the one we're after. So you design and the other competing reactions are small potatoes. That means if you measure H2O, it's mostly going to be sensitive to this one. That's about as good as it ever gets. And here's his experiment. So he measures H2O versus time. Here's the milliseconds. So it's sitting here cooking away and then it ignites. And for his experiment. And that would have been this experiment right here. So he have 1,000 parts per million of oxygen. So how much H2O can you have? You can have 2,000. Yes. So anyway, this is the best fit. It's very sensitive to the fit. So he could determine this within maybe 3%. And you plot this. This is his data in the red points that Professor Pilling was displaying, Hong. These were the earlier points from my student of 1990, 23 years ago, who used the UV. Fortunately, they're in great agreement. These other points are the best available data by another method known as HRS. they have a lot more scatter. So we agree, but we have a lot less scatter than they do. So that's a pretty successful result. We would say that this is known to maybe 5, 6, 7% now. So what's the take-home message? That laser absorption, properly executed, is a very good way to study combustion chemistry. It's so quantitative, the lasers are quiet, it's a good method. Here's a newer one. This is this reaction here. Someone did an analysis of the sensitivity of flame speed. They were looking at why don't kinetic models for hydrogen oxygen fit the flame speed data that come from places like Princeton. What's wrong? And they did it because most of the hydrogen oxygen mechanisms are so well known. And they concluded that one of the ones that they really needed to know better was this particular reaction. And so they asked if we could work on it, and I'd always thought of it as H plus H2O going this way, and I don't know how to do that exactly. But suddenly I realized that we could do a trick and do this reaction this way, and that was the answer. Okay, we do what's called a pseudo first order experiment. They're like the ultimate experiment. You do T-butyl hydroperoxide as a prompt source of OH. So it's like you instantly produce OH. And then it's in excess of hydrogen. And so the OH goes away in a pseudo first order way. This was an idea that was pioneered by Bott and Cohen about 30 years ago, sometimes used at Argonne. There's this molecule called tert-butyl hydroperoxide, which you can buy. And as soon as you heat it to like 1200 degrees, it kind of instantly becomes OH plus methyl plus this thing here, acetone. So as long as you take account of the possible reactivity of those other things, this is what you get. So this is OH, 1000 ppm of hydrogen, 26 ppm of T-butyl hydroperoxide, or hence OH. So the OH instantly shoots up to 26 ppm, and then it decays exponentially by that pseudo first order reaction. And the fit is so good. I mean, you can just measure this so well. So as long as we get 10 to 20 to 25 ppm of OH, we get really good signal noise ratios in our experiments. We claim we fit this to 3 to 5%. That leads to these results right here. Really low scatter. I always look first, what's the scatter? And if a new student tries it, does he get the same answer? Very low scatter. And now the data points are the black ones. So the good news is they agree with all the other data, but they're better. They have less scatter. So that's kind of a happy story. That means the modelers who are worried about uncertainty analysis can now put in much smaller error limits as they try to figure out why their flame speeds aren't working. That was category 1. That's the elementary reactions. Those are the best ones. But there's a lot of interest now in OH plus various hydrocarbons, because that OH extracts an H and is a critical reaction in nearly all of these cases. All of these things are called esters. Methyl formate, methyl acid. This is a progression in the size of the methyl ester. I think I'll show a sketch in a minute. And we do the same thing. We use our OH trick plus these, and we watch OH go away. We also look at pyrolysis of esters, and I'll show you that in a minute. And there we measure several species. Here we just measure OH. Here's the methyl ester. So this is the methyl formate. That's the smallest one. So it's methyl ester. That means there's a methyl on the end. And formate means there's just an H out here. If you go to methyl acetate, now we have a methyl group out here. Methyl propionate, now we have a couple of these groups, and so on. So it's a progression in size of these things. So now I'm just going to show you the answers. Here's the rate coefficient for these studies, 1 over T, starting down here with the one that's the slowest is the acetate. So interestingly enough, the acetate is slightly slower than this acetate is slightly slower than the formate. Then it jumps up to propionate because of the increased availability of H's out here. And then this one is, so basically it's all these H's that are available to react with the OH, so it progressively goes up. So this is really a very nice, accurate progression of data that's enabled. Low scatter. This student's very conservative. He says plus or minus 25%. I think it's better. Good agreement with something called the structured additivity relationship by somebody named Atkinson. Now, one question is, how well can you calculate this rate coefficient? Here's a comparison of our data with a recent calculation from Princeton. Not to knock Princeton. But the point is that for many of these things, you cannot calculate them as well as we now can measure them. So the data then becomes a way to help the modelers. Eventually, the models may be better than the experiments, and they'll help us. But right now, we're able to help them. Okay, so you begin to see there is value in high-quality data because they would guide the modelers. Okay, now I want to turn to pyrolysis. What does that mean? That means we're going to look at this molecule when it's hot without any extra oxygen, and we're going to apply multiple species versus time. So this is 1400 degrees. This is always time after reflected shock heating. This is now, I had this question before. I think this is the fraction of the oxygen. And the idea was, can we possibly track all of the oxygen and therefore be sure we know what we're doing? So initially, all of the oxygen is up here in methyl formate. As time goes on, the CO and the methanol grow linearly. At about here, the methanol starts decomposing and produces more CO. Look how nice that CO record is. It looks so good sometimes you think it's a calculation. It's really fantastic. So we measure methane or CO2. This is the early formaldehyde work. So when you do this, we can account for about 98% of the oxygen. So that makes me feel good. That means we probably are not making any significant mistake. So at 300 microseconds right here, we can track what I believe is virtually all of the oxygen. That means that we're going to constrain the reaction mechanism. They can't just measure or simulate CO. They have to also simulate they have to simulate all these species. All of a sudden, that starts constraining the people doing their tuning. They've never really had that kind of data before. So that's a new strategy. Okay, I'm going to end up on, I don't know if it's the end or not. I'm going to, 23, not quite. I'm going to show you two examples of butanol kinetics. Butanol is very popular right now as an alcohol. I'm going to look at pyrolysis. And I'm going to look at, N-butanol. That's the normal butanol, this structure. There's the tert-butanol. We've actually done there's 4 butanol isomers. We've done all 4. But I'm going to just show you the pyrolysis of this one, and then I'm going to show you the OH abstraction from this one. This is this structure. We're going to see that the problem with this one is that when OH reacts with this, it can sometimes release an OH, and it confuses the measurement. And we use something called isotopic labeling to solve that problem. Okay, so does that mean that I'm not going to talk about the first one? Maybe it does. Let's see. Okay, looks like I'm not going to tell you about the butanol pyrolysis. I'm going to focus about this isotopic labeling idea, which causes a lot of anguish. Here's the problem. There's multiple reaction sites on tert-butanol. And some of those sites, if OH abstracts an H, will cause what's called beta scission, and an OH will pop off. And if we're measuring OH versus time, all we can measure is how fast it's going away. And how do we account for the fact that sometimes one removal leads to a replacement? That's the problem. And so we came up with a strategy. I'll show you here. Okay, now, this is the tert-butanol molecule right here. And when OH reacts with it, usually we're talking about O16. So we have our laser set to measure O16. And we produce O16 with our T-butyl hydroperoxide. And the OH comes in and it attacks this tert-butanol. It has 2 initial possibilities. It can extract here, or it can extract here. Now, the nice thing about tert-butanol is, you see there's really, each one of these ends is the same. So it's like there's really only one path, not several. So it can extract an H from any one of these 3, 6, 9 sites. Since there's 9 sites that it can extract an H from, it's much more likely than this one, where there's only one H site. So we believe most of it goes this way. But we don't exactly know how much, so we call that the branching ratio. What fraction goes here? What fraction K1 over K1A plus K1B? We think it's probably about 0.9. But once that happens, now we've got this molecule down here. It can decompose by what's called beta scission, and all of a sudden it produced an OH. And we're just measuring how many OHs are there. Now how do we account for this one that just came into the game? That's a problem. So we call it, so the green, these are losses, and the green says it's a reformation. We're repopulating. That's a problem. That ratio is called BR2. That's the branching ratio. How do we solve that problem? So if we measure OH dot, removal of OH, even in the limit that most of it goes this way, we're going to be confused by this branching ratio. Some fraction of it gives us back our OH. And we're going to see a reduced OH dot. So if we look at conventional tert-butanol using OH16 measurements, we're going to be plagued by this problem. What we're going to see, you can do the algebra and you can show that ROH dot is a complicated function of the overall rate, which we're after, and these two branching ratios. So even if this one is near 0.9, we don't know what this one is. That's a problem. We kind of didn't anticipate this problem, and so we had to work for about a year. So then we realized, well, let's try isotopic labeling. So what does that mean? That means you buy some tert-butanol that's got an O18 here. Does O18 absorb at the same place as O16? The spectrum is going to be shifted a little bit. So if we park our laser and we look at O16, we're not going to see that reformed O18. So now we're going to have, yeah.
So can you just call up like Sigma and tell them you want a bottle of this stuff that has a different...
Yeah, and they'll say, send $7,000 for this little bottle.
So,
yes,
but yeah,
and by the way, we're not sure when we're going to deliver it, but it might be 3 months.
Okay, that makes sense.
And then we're shaking. Well, what's going to happen when we try this? We're not experts at this. We're going to put it in a shock tube and it's just going to fizzle away, you know, because we played with some other stuff that didn't work. So it turns out this worked really well. Yeah, you can buy most of these things, but a clever person might say, well, why didn't you label the H? Or, you know, there's some other strategies. But it turns out there's reasons against those. So let me explain how this goes. So now, if we label O18, it's still, our O16 still can remove by these two paths. But now down here, the O18 pops off instead of the O16. So what do we measure? I'm measuring the rate of removal, which is really the sum of these two reactions, which I'm after. So this is a very nice thing. So we measure, we're immune to this reformation. So now you could also do some tricks where you say also measure O18. There's some other things you can do. But it turns out there's not a lot of O18. That was hard to do. So now here's what we measure. We measure at 17 ppm of TBHP, 500 ppm of tert-butanol, and we measure 1,000 degrees. And what we see is the OH jumps up. Why does it jump up? Because it takes a while for the TBHP to decompose. Why does it go away? It's reacting with the tert-butanol. So basically this slope, although we fit it with the detailed model, this slope, which we determine within, you know, I don't know, 5%, is the overall rate of OH plus tert-butanol. That's what we're after. That's what the modelers need to test their models. So that was a great idea. It's very temperature sensitive. Let's see, what's this? Oh, this is O18. Okay, this is the unlabeled, this is the labeled. Same experiment. The labeled goes away faster. That's the answer. The unlabeled goes away slower because of the reformation. So if we didn't think about this, we'd report this number instead of this number. It would have been a mistake. Well, the reviewer would have caught it, probably. So that is the difference we're seeing. that's the advantage of using the isotopic labeling. And how do these rates compare? So now you can plot them on an Arrhenius diagram. And this is the total that we're after. This is the value that's in somebody's simulation, Manny Sarathi. There's a lot of different simulations, and they're all over the map, by the way. Now, because we've measured both, this one is the sum, and this one is the complicated function that I told you about. So now we can take the ratio of these two and solve for BR1 and BR2. BR1 is the one where we think it's 0.9. So all of a sudden we can put limits on BR1 and BR2, or at least the combination, and the modelers love this. The kinetic people who are doing the theory love this. They've never had this kind of information. So if this ratio is this quantity here must be around 0.2 because this is 1/5 of this number. And now since we know that BR1 is a pretty big number, we just solve for BR2, which is pretty well. So that's the advantage of isotopic labeling. It is expensive, it's got some subtleties, but it's a very powerful tool. I want to talk just briefly about we're always working on new species. I told you I've got a student who's working on aldehydes. I think he started in September, so he's pushing 2 years and 9 months right now to get this worked out. You usually spend more time on the developing it than applying it, because the students get anxious to leave. But the next students can use it. So we're working on measuring ethyl. We know how to measure methyl. We're trying to measure ethyl. We've done a good job of ethylene, but I really, really want to have propene and butene. We're almost ready to measure acetylene. I think we'll succeed on that one. We've got the laser now. That should go pretty fast. So we're always working on these things. You're always trying to add more species. And I'm going to show you an example with the aldehydes. The simplest aldehyde is this formaldehyde, where it means you have an H here, and the acetaldehyde you have a methyl here. Those are two aldehydes, they're called. And they're formed when you have pyrolysis of oxygenated hydrocarbons, and they're also formed during combustion of certain fuels. Here's the problem. The spectroscopy we've been talking about is diatomic molecules. Now it gets a lot more complicated. So let's look at, the first thing we ask is, where do these species absorb? So we have to look in the UV, we have to look in the IR. The red is the acetaldehyde, and the blue is the formaldehyde. And so what you see is they both absorb in the same regions. This is frequency in the infrared. So divide by this. This is around 4 microns here. So this would be 3.7 or something like that. So the acetaldehyde, being a bigger molecule, has more of a continuous distribution. The formaldehyde, being a smaller molecule, has discrete structure. And when you go over here in the UV, you can see it even better. So the formaldehyde, being a smaller molecule, has discrete structure. The acetaldehyde is more continuous. So we got two species that are usually present together. What do? You have to use at least 2 colors, maybe 3. And so if you do that, you can maybe figure out a way to measure everything. We are using 3 right now. So let's see. We measure at that wavelength and right next to that wavelength. So we kind of go on and off that peak. That's going to be mostly sensitive to formaldehyde. And over here, we measure kind of where the red is kind of between the blue. It's mostly acetaldehyde. But in both cases, you have to worry about the competition. Yes?
So were you scanning?
No.
Through?
Well, okay. Sometimes we repeat the experiment. Sometimes we scan during the experiment.
Wow.
So sometimes we dither the infrared laser on and off fast. Other times we just park the laser and repeat and if we only have one laser, we repeat the experiment. Or we use 2 lasers. So there's different strategies.
So with that UV graph, were you able to quickly scan that way, or?
You mean, where do we get this graph?
Yeah,
Okay.
or the UV one on the other side too. Like, were you able to scan through that whole thing during a test, or?
some of these would have been calculated, some would be measured. Okay, that's room temperature. That is already available in the literature.
Okay.
The runs at room temperature you can find in the literature.
Okay.
When you get here to 1200, okay, that's in the literature too. So we took these from the literature.
Okay.
Now, and that's good enough to pick our colors. It's not good enough though to be quantitative. So then, okay, unfortunately I skipped over this. Having picked those colors, the student then spent 6-9 months doing controlled experiments at each of those 4 colors. 4 colors? 3, I guess. There's going to be 4 eventually, but we use 3. And at each of those colors, we have to measure the cross-section as a function of temperature and pressure. So we build our own spectroscopic database of the absorption coefficient of both species at all 3 colors. Then when you make an experiment and you measure the absorption at all 3 colors, you got 3 measurements, you can sort out 2 quantities and check yourself. But only, so this is just to pick the colors. That took a long time. Then he did the experiments to measure the cross sections at each of the colors as a function of temperature and pressure. So there's a lot of work that goes into getting this ready. Now then he has to check himself. And so we have to have a way to produce these species. Here's his experiment. He heated something called trioxane. Trioxane is something you can buy, which when it comes apart produces formaldehyde. You also can buy the acetaldehyde. So now he does an experiment here with 0.167% trioxane. That means as soon as it comes apart, you're going to get 0.5% of formaldehyde. And so on. So here's the results of an experiment at the 3 colors. And from these, you can deduce the mole fractions, which should be a constant value for the red is the acetaldehyde. It should be constant because we started with acetaldehyde. But the formaldehyde takes a while to form because we started with trioxane. So the good news is we got the right answer. We can sort it out. We can get both species simultaneously, and we can also study the decomposition of trioxane if we want. Now he's ready to use this. 2 years and 9 months, I'd say. But this is that was a pretty hard problem. Why? Problems are always, it's always interference absorption. With small molecules, you can sort it out. Big molecules, it's a problem. We're also working on HO2 and H2O2, same problem. So I'm going to, okay. So my message is, I thought there was more words on here. Laser absorption and shock tubes go together. If you have quantitative species measurements in a controlled environment, you can do really world-class chemistry. Questions? Yes?
In what environment and how did you measure HO2?
Okay. So HO2 has some infrared bands, but I favor the UV bands. So the trouble with HO2, it's hard to do chemistry, if you said in Pilling's lecture. Yeah, I think he said this. It's very hard to do chemistry on HO2 and H2O2. You can't, they're hard to handle, they're hard to produce, reactive, it's a problem. Most of the work that's been done on the chemistry of those was done in Germany by Tro's group. They used UV absorption. They used a couple of different colors. They didn't have access to the lasers that we have. So we've looked in the infrared, but I like the UV. And so right now we're working on, if you work around 220 nanometers, that's a good place to measure HO2 and H2O2. So we measure, basically, it's a 2-color strategy, 220 and 245. So the spectrum, the relative spectrum changes for those species, and that's a pretty sensitive way to go. And there, the absorption cross-sections are fairly well known. But otherwise, that's a problem. How do you produce a known amount so you can measure the absorption cross-section? It's a dilemma. So spectroscopy, and so if you can generate a known amount of stuff, you can measure the spectroscopic parameters. But if you know the spectroscopic parameters, you can say how much stuff you have. It's a question of which hand helps the other. So, but we worked on HO2 some years ago. We're coming back to it again because there's a lot of interest in low temperature chemistry and peroxide chemistry. A lot of interest. and an oxygenated species. So we're getting ready. We're getting close to being able to do. So the shock tube gives us great control over temperature. We just have to have good sensitivity for species, and we have to deal with interferences. Yes?
So, two questions I have. First is, does vibrational relaxation affect your species measurements? And second is, how much do you have to account for variation of temperature throughout your test time in reactive experiments?
Good. Does vibrational do we have to think about vibrational relaxation? And does temperature change affect us? Yes, yes. So, vibrational relaxation. Usually, so incident shock goes by, heats you to T2. Reflected shock comes by, heats you to T5. T5 is approximately 2 times T2. Almost everything goes a lot faster at T5 than T2. So unless you spend a lot of time at T2, you'll almost always see the action in region 5. Unless the action is too fast to see, and then it'll be. So you can design an experiment where everything happens in region 5 for chemistry. Usually, the vibrational relaxation is much faster than the chemistry. So usually, when you watch the chemistry in region 5, you can assume that the vibrations are in equilibrium. There are some exceptions. The trickier question is, when reflected shock is going back into region 2, should you assume frozen or equilibrium vibrations? Now it depends on the mixture. So you have to kind of know the results of past work. You have to kind of be able to calculate this and decide what regime you're in. Or you have to check it. Let's see. So that's a good question, but you have to use your head. But you can usually arrange things so that the vibrations are in equilibrium. Or you can study it like what we're doing. We design an experiment, no chemistry, only vibration relaxation. But the reason we're doing this is because there's a really big unsolved question. You can plot the vibration relaxation time versus temperature, and the dissociation rate of oxygen versus temperature, and they start to cross over at about 9,000 degrees. No one has figured out how to do a good experiment at about 9,000 degrees. So we're going to work our way up. For a long ways, the vibrational relaxation will be much faster, and we'll have a Boltzmann distribution. The dissociation will be slower. We're going to measure both. What's interesting is what happens when they start getting close. And I think what that means is that the dissociation is going to rob from the upper manifold of the vibrating oscillators, and it's going to slow the vibration relaxation down. So I think what we find is you get into this mixed regime, vibrational relaxation doesn't quite finish because they're being drained off to dissociate. That's the most challenging, hard, nobody's ever done it, experiment. But usually that's not the case. Usually the vibration relaxation is very fast. And if you have hydrocarbons, the vibration relaxation is so fast. Usually it always takes the path of least resistance. So if you have a little water, you have some hydrocarbons, they'll relax almost all the species pretty fast. So it's not too hard to be in a regime where vibrational equilibrium can be assumed. You can always check it, but you're almost always safe there. The second question is a trickier one. Do you have to worry about temperature change? Absolutely. Why? Because it affects the chemistry, but it also affects the absorption coefficient. So if we measure absorbance versus time, and we want to convert it to mole fraction versus time, it's simplest if the absorption coefficient is a constant. If it's not, I've got to have a way of accounting for temperature change, which is why we spend so much time learning how to measure temperature. Turn that phone there. Okay. So that's a good question. So we have to pay a lot of attention to temperature change because it affects the chemistry, but it also affects our measurement. If you neglect this, so this is why, and your advisor knows about this, this is why if you use too much fuel, you're going to have, even if you have everything else under control, you do pyrolysis, oxidate, you're having temperature change, and you have to account for it. So you measure absorbance, but you want mole fraction. So it's a problem. But you know what it is. We can get around the problem. But that's a good question. Anything else? So let's see. Okay, tomorrow is all fluorescence. We'll talk about fluorescence. Fluorescence is absorption followed by emission. So we do absorption first. What happens to the absorbed photons? The absorbed photon causes a molecule to go here. What happens? Usually a collision tells it to go back. Usually. That means you're heating. But sometimes it will re-emit. And that photon goes out into the world. And you can measure that. And the virtue of that is that you can do spatially resolved measurements at the price of it being hard to make quantitative. So if you want spatial structure, you get it. And that's the basis of the method known as PLAF that was developed in my laboratory. So we'll talk about the basic ideas of laser-induced fluorescence and then planar laser-induced fluorescence tomorrow. Okay, thanks.